Thanks for the nice introduction, Holger. I'm Till, and I work at Bavarica. There I spend most of my time working on the distributed coordination and the backend components. And today I want to tell you a bit about what happened in the backend area and what the community is currently working on. All right, let's get started. So first, I'd like to talk a bit about the improvements the community did to the scheduling and failover of Flink jobs. To begin with, I'd like to recap one of Flink's goals. I'm pretty sure that you've seen this, or heard at least this a couple of times by now, but still, it's very important. So one of the goals of Flink is to unify batch and streaming, batch processing. The motivation for that is that batch is actually can be seen as a bounded stream, and thus is only a special case of stream processing. And if we have like a single system which is able to process bounded as well as unbounded streams, it eases operations, it unlocks new use cases where you have mixed workloads, or it allows you to process historic as well as real-time data with the same job. However, is it all that simple? In order to answer this question, let's take a look at how Flink processes streaming and batch workloads. So let's start with the streaming workload. So since a streaming workload is usually unbounded and produces continuous results, the first thing Flink needs to do is to bring up all tasks. Once all tasks are running, the system can start. Sorry, wrong direction. Can start reading from the external system. At some point, we need another mechanism which tells us that we have seen all the data up to a certain point, which are the watermarks. And this basically signals the system that it can now output results up to this point. And as the data arrives and more data is read and processed, more and more results are being output. And this goes on for potentially an infinite amount of time. In contrast to that, a batch job is executed a bit differently. So first of all, we don't have to schedule the whole topology. We can start with the sources. Since all the data is available at the start of the job, we also don't have to read the data in the order it arrived. Instead, we can read it in an arbitrary order, potentially in a massively parallel manner. Once we have read all the data, the watermarks, like conceptually, instantaneously jump from the beginning to the end because we have seen now all the data and we can output the results. If this now happened for the sources, it will effectively trigger the execution of the next stage. Here, the same happens. All the data is being read, and new results are produced, which are finally given to the sink, which outputs the result at the end of the job execution, where the result becomes visible. The reason why the execution of a streaming and a batch job is so different is that that we can exploit the property of boundedness in order to execute the batch job more efficiently. So, for example, one thing I've already mentioned, we can read the input data in a massively parallel, out of order manner. Latency for batch jobs is not all that important, so we can also employ a more efficient batching of records to increase the throughput. Also in the boundedness, or in the bounded stream case, we can use some optimized operators which exploit this fact. So, for example, if we have a join operator, instead of using like a simple hash strategy, we could use a sort merge join operator to do that. And also, since the user usually cares only about the results at the end, once all the data is processed, we also don't have to deal with watermarks or incremental results. And as we have seen, the different stages of a job can be executed one after another. which in some cases can mean that we use our available resources more efficiently. And this stage-wise execution will actually become relevant for the next things I would like to talk about, which is the improved failover. So with Flip 1, which is the very first Flink improvement proposal, we implemented fine-grained recovery. This feature has been released with Flink 1.9, so it's out there for a couple of releases already. And the idea of this on how to improve recovery is that that this feature tries to avoid redundant work in case of failovers. So the batch job is separated into different stages, which in our case are defined by the so-called pipeline regions, which are regions where the operators are connected by pipeline data exchanges, meaning that all operators have to run at the same time. These pipeline regions produce results which the system tracks and uses for failover. So instead of if at the latest stage of your last stage of your job a fault occurs, it won't restart the whole topology from scratch, but will backtrack to the latest available result. So let's take this small example here where we have a source and a mapper and a sink, and we start with the execution of a source which produces the result. Once the result is completed, the mapper will be scheduled, which again will produce a result. And last, the sink will be scheduled to produce the result, only the final output of the job. If now, like a fault occurs, what needs to be done is not to rewind the job to the very beginning, but to simply reschedule the sink operator to consume the map result again in order to finalize the result. And thereby, we save a lot of work and time, which speeds up the overall execution of the job. In order to measure the effect of this feature, we've taken the TPCH query 3, which is effectively a three-way join with a subsequent group by operator. And we run this job with some where we induce some artificial failures with the which were following an exponential failure rate distribution. And we took this job, executed it once in a pipeline mode, meaning that all the operators are connected by a pipeline data exchange, and the system tries to bring them online at the same time, which also means that if a fault occurs at any of the operators, the whole topology needs to be restarted. These are the red bars on the right side. And we also run the job in a batch mode where the shuffle operations, so the operations which feed data into the joins and the group by operators, are executed in a blocking manner, meaning that they break the pipeline and define several pipeline regions which are executed one after another. As we can see in the diagram, is that the batch mode execution degrades much more gracefully as the failure rate increases, or the failure frequency in seconds decreases, which is effectively the same. This, if you think about it, might not be. First of all, it proves that Flip 1 improved the execution of batch jobs under faults, but might not come as a big surprise, given that in the pipeline mode, what we're actually doing is we execute like a single large stage where we need like a rather long window where no fault occurs in order to successfully complete it. Whereas in the batch case, we have smaller chunks of the job where we only need smaller windows without no fault in order to make progress. And that's basically what Flip 1 enables you. All right. How can you benefit from this feature? So first of all, since it has been introduced with Flink 1.9, you have to use Flink 1.9 on your or in your version of Flink. When you use the table API or SQL and use the Blink table planner, then you can already see the benefits of Flip 1. However, if you are a dataset user, there you have to enable it explicitly. By default, Flink tries to run the dataset jobs in a pipeline mode, where you won't see the benefits of Flip 1. Instead, what you have to do is you have to set the execution mode in your execution config to either batch, which means that the shuffle the shuffles in your topology will be executed with the blocking data exchange or like a pipeline breaker, or you have to use the execution mode batch forced, which means that every connection is actually using a blocking data exchange. This effectively breaks up your job into the smallest parts possible, which also means that it behaves most gracefully under faults. All right, so much for the failover. We will see in the following slides that we will encounter the pipeline regions again for the scheduling. But first of all, first let's take a look at the existing scheduler and what kind of problems it has. So Flink's old scheduler works the following way. The scheduling strategy is called lazy from sources, because it orders your execution graph in a topological order and schedules all the tasks where all the inputs of these tasks are ready. And as more and more tasks are being executed and complete, they complete the inputs for other tasks, which then become schedulable. The thing is that the scheduling strategy only takes a look at the task itself and its inputs. It does not consider other tasks which might need to be executed at the same time, and this actually leads to problems. So take as an example this simple join operation where we have like a customers operator which is joined against orders. So the customers operator is connected to the join operator with a blocking data exchange, which means that it needs to finish before the join operator can run, and the orders operator is connected in a pipelined way to the join operator, which means that the orders and join operator need to run at the same time. Now, if Flink is asked to schedule this topology, it can do it in two ways. So it can start with the customers operator or with the orders operator. Now assume we only have a single slot available, because then it makes actually a big difference which of these operators we schedule first. Assume, like in our first scheduling plan, we start with the orders task in the single slot. Now also assume that the join operator can actually share the slots with orders. So in order for orders to complete, the join operator needs to be scheduled as well. But for the join operator to complete, it actually needs the customers operator is scheduled. But since we only have a single slot, the customers operator can no longer be scheduled. We effectively end up in a deadlock situation because we chose the wrong scheduling order. If we started with the customers operator first, we can actually successfully schedule this kind of job, showing that the existing scheduling strategy is suboptimal. And the problem of this scheduling strategy is that it ignores the input constraints of tasks which need to run at the same time as the task which is currently scheduled, as we have seen with the join operator. So the way we solved this problem is that we changed the scheduling unit, or extended the scheduling unit from tasks to the pipelined region. And again, a pipelined region is the set of tasks which have to run at the same time. And a pipelined region is only scheduled if all of the operators in this pipelined regions can get a slot and can be deployed. So either all or none. So now when using like the pipeline region as the basic scheduling unit, there's only a single valid plan we can schedule this topology. So first of all, we have to deploy the customers operator, because the pipeline region in which the orders and join operator has an input dependency on this on the customers pipeline region. And then once this pipeline region has completed, we can run the orders and join operator to successfully complete the execution. So what are the benefits of the pipeline region scheduler? So first of all, it gives us more reliable scheduling of bounded jobs under constrained resources. So this means if you want to run a bounded job or batch job with a higher parallelism, then you have actually slots in your cluster. This is possible as long as the largest pipeline region in your topology can be run on your cluster, and it will guarantee you that it will not deadlock. And by making sure that only tasks are being scheduled which have no pending inputs, so where all the inputs are completed and ready, we actually can also improve the resource utilization, because it won't happen that we schedule tasks which actually idle around because they are still waiting for one of the inputs. It can make no progress. And that's the benefit of the pipeline region scheduler. Now, bringing all the pieces together, what we've seen is that the pipeline regions are actually the basic unit for scheduling and failover in Flink. And it actually also generalizes quite well with respect to streaming, because you have to know that at the moment, we have two different schedulers or scheduling strategies, one for bounded streams or batch jobs and one for streaming jobs. For streaming jobs, the scheduling strategy works by acquiring for all the operators or trying to acquire slots for all the operators. And if this is possible, then scheduling the job, and otherwise failing. If we now think about a streaming job and think about the pipeline regions of this job, we actually pretty quickly come to the conclusion that there is then only in a streaming job a single pipeline region. And this pipeline region just happens to produce potentially an infinite amount of results, so needs to run all the time. As I've said, the pipeline region scheduler tries to schedule all of the operators in a pipeline regions or none, which is effectively the same as the all at once or eager scheduling strategy which we currently have in Flink. So actually, this pipeline region scheduler can replace the existing scheduling strategy for bounded as well as unbounded streaming jobs. All right, so much for the work on the failover and scheduling. Now let's talk about what the community is currently working on, which is elastic streaming pipelines, or enabling Flink to react to changing workloads. The practitioners among us, probably know it better than me. But when you run a streaming application, which can last potentially for can run for weeks, months, and even longer, one actually faces the problem that over time the workload can change. So, for example, if you run like a hiking app, then you might see a seasonal change in the usage, because during spring or summer more people are hiking. If your app manages to get on Hacker News on the front page, you might see on a random day like a huge increase of new users, for example. Or if you're running like a service or product for companies, you usually see a decline in usage over the weekends. Or if you're just good at what you're doing and successful, and more and more users are starting using a service, you see a steady increase. So what all of these things have in common is that it's quite hard to decide on the required resources to fulfill your services with a given degree of quality upfront. So at the moment, what Flink can only give you is that at deployment time you decide on the parallelism with which you want to run the job, and then it's fixed over the lifetime of the application until you stop it. This has the problem that if you over provision, then you're wasting money, and if you under provision, then your service quality degrades, which is also not good. So ideally, what people are interested in is that the available resource of Flink scales with respect to the actual workload, so to minimize the over and under provisioning. Before we take a look at how we want to solve it, I first have to introduce a bit of terminology here. So in Flink, Flink supports many different deployments, different deployment types, and one way to distinguish deployments is whether Flink knows about the underlying resource manager or not. So if it knows about where it runs, that's what we call active deployments. And this usually means that, or this means that Flink is able to talk to the underlying resource manager. For example, this is the case in Yarn, Mesos, or when you use the native Kubernetes integration. And thereby, Flink can ask for more resources if it sees that it needs it. In contrast to that, the other deployment mode is the oblivious deployments. There, Flink does not know where it runs, and it only can work with what it was given by let's say, for example, the user when he started the standalone deployment, or when running in a containerized environment by some third-party tool or autoscaling groups, for example. So since we want to make these elastic streaming pipelines work in both deployment modes, what we at least have to support is that we can react to newly arriving resources and make use of them. And this basically gave birth to the idea of the so-called reactive execution mode. The reactive execution mode works the following way. So when we start the job, we will spawn a job master responsible for running the job and the resource manager. So the first thing which happens then is that the job master tells the resource manager that it needs as many resources as it can get, because we want to react to potentially new arriving resources. If now a task executor is started and registers at the resource manager, the resource manager will see that there's a job with an infinite amount of resource requirements. So it will assign the available slot to this job master. And after some time, if the job master realizes that no more resources will arrive, it can actually start executing the job. And here it only got one slot, so it can run it with a parallelism of 1. If now at a later time, another task executor arrives and registers 2 more slots at the resource manager will see, okay, I haven't fulfilled the resource requirements of this one job, so I will also assign these 2 slots to the job master. And by assigning these slots, the job master can make the decision to scale the job up, to run it now with a parallelism of 3, thereby effectively making use of the newly available resources. All right. What do we have to change in Flink to make this happen? So the first thing you might have noticed is that we need to tell the resource manager that we need all the resources it has. With the existing slot allocation protocol, however, this is not easily doable. The problem is that with the existing slot allocation protocol, we ask for every slot individually. So whenever a task is supposed to get scheduled, we need the slot and ask for it. And if we cannot obtain the slot, then we fail, and this usually triggers a recovery. So if we ask for an infinite amount of resources, which are potentially fulfilled at a very late point in time, this obviously won't work. So what we came up with, and the solution to the problem is to change the let's say eager slot allocation protocol into more of a declarative slot allocation protocol, where the system announces how many resources it wants, but it doesn't fail if it gets less. So the resource manager will then try to fulfill these requirements as good as possible. In the case of active deployments, it can even start new task executors if it sees that the existing ones aren't sufficient to fulfill all the requirements. And then in order to get this reactive mode where all the slots will be made available to the job master, we simply have to tell that our resource requirement is integer max, for example. That way, the job master will get all of the available resources in the cluster. And this work started. It is done under the flip 138 called Declarative Resource Management, and we hope that we can finish it with the release 112. All right. The next step to make the reactive mode happen is that we also need to make use of newly arriving resources. And for that, we have to touch the scheduler. So the old scheduler works the following way, and there you will quickly see why we cannot really use it. It gets the job graph when the job is submitted, and the user usually also defines the parallelism with which it wants to run the job. So it's kind of predetermined. Then the system asks for the resources. If it gets the slots, then it executes the job, and if not, because if there are not enough resources available in the cluster, then it will simply fail. What we have to change is to make use of this declarative slot allocation protocol. So a declarative slot scheduler should work the following way. First, it takes a look at the job it's supposed to execute and declares what kind of resources it needs to run it with well, as good as possible. At this point, we haven't decided on the parallelism yet, and this is important because we wait for the resources to arrive at the job master before we decide on the parallelism, and thereby we basically invert how the old scheduler did it. And yeah, that way we can basically react to to situations where we don't get everything we need. And last but not least, we need to adjust the parallelism if more resources arrive later. So how would this look like? So let's take as an example the simple job graph where we have a source and a sink. Additionally, let's assume that the operators or the tasks want to run in their own slots. So the scheduler wants to run it with a parallelism of 2, so it tells the system that it needs 4 slots. If it only got 2 slots, then can make the decision, okay, fair enough, I can still run the job, it's better than doing nothing, but only with a parallelism of 1. If at a later point the 2 missing slots arrive, it can actually make use of it. And how can it do it? Similar to what you do at the moment manually, taking a checkpoint and restarting the job from this checkpoint, and thereby making use of the now available or additionally available resources, which means that now we can run the job with a parallelism of 2. Yeah, and that's it basically. This is the idea, or the 2 building blocks which will enable this reactive mode, being able to react to newly arriving resources. And actually, we can even extend it and give the Flink job like the control to control the parallelism of itself, which is effectively, or which is auto-scaling. So the idea here would be that every operator has something like a rescaling policy, which tells the system which parallelism it would like to run. So this would then be like the target or the target parallelism, which the system tries to achieve. And if this rescaling policy can be user defined, then the user or the user can decide on how it behaves. The rescaling policy will be periodically triggered by the system to gather like the resource requirements, which are then given to the resource manager. So in this case now, if the first operator says that the target should be 2 instead of 1, we would update our resource requirements. And once the third slot arrives, we let the declarative scheduler make use of it by effectively scaling the source or the first operator to a parallelism of 2, and thereby achieving like auto-scaling. All right. So this brings me close to the end of my talk. So what are the benefits of this elastic streaming pipelines? So obviously, Flink can make better use of resources and decrease the under and over provisioning, which at the end of the day will save our users money and allows to guarantee a certain service quality. By being able to add resources on the fly to a cluster and let Flink make use of it, as well as tolerating disappearance of task managers, I think we also will improve or ease operations. And with the reactive mode, I think we get a step further towards more of an application-style deployment, where you can deploy or run a Flink job as simple as starting a process on your machine. The idea here would be that the processes will connect to each other and figure out who is the current leader and who are the followers, and then with the reactive mode, making use of all the available resources. And so you would basically get rid of managing a cluster, which is really nice. All right, this basically brings me to the conclusion of my talk. So what have you seen today? So you've seen that Flink has now a unified scheduling and failover for batch and streaming, which improves the scheduling performance and the failover behavior of batch jobs. Moreover, the community is currently working on the fully elastic streaming pipeline support, which will enable Flink to better handle changing workloads. And last but not least, the reactive mode will ease operations and deployment significantly, we believe. And with that, I'd like to thank you for your attention. Before we get to the question, just a quick note: if you like what we're doing and would like to contribute to it and get paid for doing it, then please apply at Bavarica. We are currently hiring. Write me or go to our careers page to apply there. All right. Thanks a lot. So there are now questions. All right. Is the accommodation of the newly acquired resources done via save points or checkpoints? Okay. So the question is how are we going to rescale once the new resources are there? And this will be, given that checkpoints are rescalable, we'll use checkpoints. So at the moment, when you do it manually, I believe you will do it via save points. So with checkpoints, this operation is potentially cheaper because we don't have to go through like the generalized path of save points. All right, then let's continue with Rob's question. Given these capabilities, what is your take on the current conversation around Kappa versus revisiting Lambda versus hybrid approach with a shared API? Good question. I think what like the Flink project has as a goal is to give like a provide like a computing platform for a diverse set of applications. Ideally, everything can be done under the hood. Wait. They moved to published. Moved under the hood because it simplifies operations and enables by being able to do different processing under the same hood. It enables more use cases, I believe. Yeah. All right. Niels' vote question gets upvoted, so let's try to answer this next. When do you hope the dynamic scaling will become available? Yeah, so the declarative resource management should be, or we aim to make it part of release 112, and I hope that we can make the whole feature, like the reactive execution mode, available with the next release, like 113 ideally. Realistically, I think it will probably be first like kind of an experimental feature with some limitations, but I hope that that the basic functionality that you can start processes which join the cluster and that Flink makes use of it will work. This would be my personal goal. All right. Good. The next question is from Kars. What happens when resources die? Will the job scale down automatically too? Yes. This case is doesn't work as gracefully as upscaling because a loss of resources can happen at any point in time, right? So the way we think it will work is effectively through like a recovery cycle. So assume like a task manager dies, Flink will notice that, will fail the respective task, and try to reschedule it. If it has the resources to immediately reschedule it, this works fine. If it realizes that there are not enough resources, then it actually needs to cancel all tasks belonging to the operator, where a single task failed, in order to rescale it. So it will effectively then take again a look at how many resources do I have available, and decide again on the parallelism with which it can run it, which of course will also mean that it will resume from the latest available checkpoint. All right, then Ethan asked a question about when the new scheduler is used, what happens when two jobs compete for resources? Does the second one need to wait for the first one to finish? This is a very good question. So the question effectively aims at how do we distribute resources if we have a session cluster, if we have running multiple jobs on the same cluster? So the main target for the reactive execution mode is streaming applications. So for batch, it's not all that important. And with that having said, I think the best the best deployment mode for batch jobs, for streaming jobs, is the per job mode, or the application mode, where you have a dedicated cluster for a job, and there you don't have the problem because there's only a single job. If, however, you want to use this feature on a session cluster, then the resource manager needs some kind of policy how to distribute the work. At the moment, or distribute the available resources, sorry. And at the moment, we think about just doing like a simple strategy by trying to fulfill the requirements of the first job and then do it for the second job and so on. But at a later point in time, I could easily imagine that we will have some rebalancing strategy, which rebalances the resources across the scheduled jobs. One might even sets like priorities, but with that, Flink will become more similar to a resource management system than like a processing engine. So ideally, I would like to avoid having to do this. All right, this basically leads to the last question by Yoon. How fast we can do the failover when new resources are available? Any plan that we can achieve the failover with a few seconds, as some application can only afford a few seconds downtime? This is also a very good question, and this is pretty much depends on the actual job. So if you have a job where which is like which uses a lot of state, for example, then obviously a rescale can be quite expensive and take a lot of time and induce a lot of downtime. At the moment, the reactive mode won't try to solve this problem. So we will be kind of limited by what the taking a checkpoint and resuming from a checkpoint functionality gives us. In order to give a bit more control over the rescaling, what we think is we want to expose like kind of a hook where users can basically signal when it's okay to rescale and when not. Because for Flink itself, it's super hard to reason or to have like a generalized mechanism which can reason about an arbitrary job. So it's easiest from Flink's perspective to outsource this decision to the user, because the user knows about the application logic, knows about the SLAs, for example, which the system needs to, or which you would like to achieve. So asking the user, can I rescale? For example, like sending like a request to an external service would be easiest. In order to like to further decrease or to speed up like scaling up or in general recoveries, I think we have to do a bit more work. So I think this relates to the so-called zero downtime upgrades feature, which is quite connected. So one idea could be, in the best case, Flink knows that it wants to scale up, gets the resources, and then looks at what state do I have to distribute to the new task managers. So kind of pre-warm the task managers so that you can quickly deploy the new task to this machine, and the state is already there locally. Even better would be if you could if you kind of could deploy like the new task, but effectively you're not using it yet. But you can once the task runs, you can start like sending like the state updates from the operators whose state you're gonna take over to this task, which applies it locally. And then when a checkpoint barrier arrives, you basically turn the additional task on to start with the processing of a part of the stream, which before went only to a smaller set of tasks, and thereby you have kind of I believe a very smooth way to scale up, for example. However, until this is ready and works, I think we will have at least another Flink forward, if not two. Yeah. All right. I hope I've answered all of your questions. Thanks again for your interest and attention. If you have other questions, then feel free also to write me personally, or maybe we chat in the lounge, as you like. I hope that you continue enjoying the conference, and